Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we're leveling up.
We certainly are.
If you thought analyzing a simply supported beam was complex, wait until we dive into beams that are curved, tapered, sitting on squishy foundations, and pushed right up to the point of catastrophic failure.
That's right. Every structural analysis begins with a beautiful set of ideal assumptions, whether we're talking about material uniformity or simple point supports.
The textbook world.
Exactly. Our goal in this deep dive is to equip you with the specialized knowledge needed when real-world conditions like axial loads, non-uniform sections, or extreme curvature break those foundational rules.
Yeah.
We are moving from the safe, idealized world straight into high-stakes, practical engineering.
Okay, let's unpack this. Our mission is to take a shortcut through the heavy lifting. We're starting with the fundamental mechanical assumptions for the common case of straight beams and quickly progressing into complex situations like beams on elastic foundations and the ultimate limit plastic design.
Right. We need to know what tools to pull out of the toolbox when the basic rules stop applying.
So before we get fancy, where do we start?
To appreciate the complexity, we must first respect the idealization. The cornerstone of common beam analysis is the flexure formula fiber stress equals negative my divided by I. It's elegantly simple, but that simplicity is predicated on three crucial assumptions.
Tell us what those red flags are, the things that, if violated, make the analysis immediately suspect.
Okay, the first is material uniformity. The beam material must be homogeneous and possess the same modulus of elasticity, E, in both tension and compression.
So no weird composites or materials that behave differently when you pull versus when you push.
Exactly. Second, geometry matters immensely. The beam must be straight or nearly straight. If there's a slight curve, the radius of curvature must be at least 10 times the depth of the beam.
And third,
The cross-section must remain uniform along the entire length.
and if that curve-to-depth ratio, say, drops to 5:1, we're already in trouble, potentially seeing calculated results off by 5% or more.
Precisely. Now, even under ideal assumptions, we are calculating two primary types of internal stresses. The longitudinal fiber stress, S, which is tensile or compressive, and then the shear stress, T.
And fiber stress is usually what we worry about.
In slender beams, yes. But remember that short, stubby beams, or those with very thin webs, often fail due to longitudinal shears. It's always there.
This brings us to the geometric foundation of all beam deflection analysis. The core idea governing deflection and slope is the radius of curvature.
Indeed. We established that the radius of curvature, R, is directly proportional to the stiffness of the beam EI and inversely proportional to the applied bending moment.
M, which gives us the big one.
The general differential equation of the elastic curve. EI multiplied by the second derivative of the vertical deflection, y sub c, with respect to x, equals the moment m.
That equation is absolutely essential because it is the mathematical key to solving for deflection in any elastic beam. What does that equation tell the engineer?
It connects the geometry of the curve, the second derivative, directly to the internal forces. And of course, we build on this. We know the shear, V, is the derivative of the moment with respect to x, and conversely, the moment m is the integral of the shear V dx.
Right, so you can move seamlessly between load, shear, moment, slope, and deflection.
That's the ideal.
Okay. Standard analysis assumes uniform cross-sections, which is often great for manufacturing simplicity, but what happens when a designer needs to vary the depth or width, perhaps for aesthetic reasons or simply to save weight? We're talking about tapered beams.
Tapered beams are a very common challenge. If the moment of inertia, I, varies significantly along the length, say if I varies as the quantity 1 plus kx divided by L raised to the power n, you can't use the simple deflection formulas.
So you're stuck.
Not quite. Engineers turn to tabulated coefficients, specialized multipliers found in technical tables.
That sounds like a lot of coefficients to track down and manage, especially for complex loading scenarios. Is there a more intuitive way to model this variable stiffness?
There is, and this is a fantastic practical nugget. You can often simplify the problem dramatically using an equivalent loading technique.
Go on.
Imagine a simply supported beam that is stiff in one segment, with moment of inertia I2, and less stiff in another, I1. Instead of solving the complex geometry, you model the entire structure as having the stiffness of the stiffer section, I2.
So you just pretend the entire beam is uniformly stiff. How do you account for the weaker segment?
You adjust the load. You increase all loads acting on the portion with the smaller moment of inertia, I1, by the ratio of I2 divided by I1. By substituting an equivalent magnified load onto a simpler constant section beam, you get accurate results.
That transforms a geometry problem into a simpler loading problem. That
Yeah.
is genuinely useful.
It's a great trick.
Now let's pivot from geometry to support. Most textbook problems feature supports at discrete points, but many real-world structures like pipelines, footings, or railway tracks rest on ground or material that yields continuously. Hello, elastic foundations.
Elastic foundations are defined by one key characteristic. They develop continuous reactions proportional at each position along the beam to the deflection of the beam at that position. It's a distributed restorative force.
And crucially, this model is robust enough that even discontinuous foundations, like a rail supported by periodic crossties, can be analyzed this way.
They can, provided the supports are close enough specifically, if you have at least 3 concentrated reaction forces in every half wavelength of the deflected beam. The entire analysis is governed by the foundation modulus, which gives us the characteristic constant, beta.
And beta is.
Beta is equal to the fourth root of the quantity B0 K0 divided by 4 EI.
So beta captures the relative stiffness of the foundation versus the stiffness of the beam itself, correct?
Exactly. But here is a critical limitation for you. While the complex formulas derived for finite-length beams on elastic foundations are theoretically sound, they come with a computational trap. You must not use them when the product of beta and the beam length, L, exceeds 6.
Why the hard limit at beta L greater than 6? Is that a structural failure point?
No, it's a mathematical failure point. When beta L gets large, the calculations require subtracting 2 very large numbers that are nearly equal.
Ah, a round-off error issue.
A severe one. It can introduce huge errors, especially in simpler software. You end up with grossly inaccurate results, even if the physics are right. It's a classic example of computation compromising theory.
That raises an important question. What if we introduce a force running straight down the middle of the beam, an axial load, P, while it's bending? We now have combined loading, and this is where standard superposition breaks down.
This is where things get nonlinear. Axial tension tends to straighten the beam, which actually reduces the overall bending moments. Conversely, axial compression amplifies the bending moment and deflection.
The compressive load is effectively working to push the beam further out of line.
Precisely. So if tension reduces the moment, you can't just calculate the moments separately and add them up.
Because the axial load affects the deflected shape of the beam itself.
It's an interactive effect.
Yeah.
The maximum normal stress is still calculated using the familiar combined stress formula. S max equals P divided by A plus or minus MC divided by I. P is positive for tension, negative for compression. But the M here is the moment from the combined effect.
And this leads to the modified superposition rule. What's the practical implication of that modification for a designer?
The implication is clarity in calculation. The total moment or deflection must be found by adding the moment for each transverse load combined individually with the entire axial load. You have to sum up the transverse load effects and then add the axial effect at the end.
Got it. It has to be factored in for every individual bending scenario.
Right.
Speaking of ultimate failure under compression, what happens when a key component of an I-beam under heavy bending decides to fail like a column instead of through simple yielding?
That's the danger of lateral buckling. It typically targets the compression flange of an I-beam if it's insufficiently braced. The flange, acting like a slender column, just buckles sideways.
Long before the material might have actually yielded from the bending stress.
Exactly. If you have a long, heavily loaded beam spanning a factory floor with no lateral supports, this is the mode of failure you fear most.
And our sources give a specific approximation for the critical compressive stress, S0, for standard I-beams in this scenario.
Yes, the critical compressive stress, S0, is approximated as 40,000 minus 60 mL divided by R. That M coefficient is key, as it depends on how the beam is supported and loaded.
How so?
Well, if you have a cantilever with a load at the end, M is 1.000. But if you have a simply supported beam with a midpoint load, M drops to 0.500, which indicates a better moment distribution resisting buckling.
Okay, time to tackle geometry again. But this time, the beam is curved in its resting state. Think crane hooks or specialized machine linkages. Curvature fundamentally changes the math.
It creates a nonlinear stress distribution even within the elastic range. The critical insight here is that the neutral axis shifts inward toward the center of curvature.
Ah, so the formula S equals my divided by I is no longer strictly accurate.
It's not. The assumption of linear strain distribution is violated. The forces are no longer balanced symmetrically around the centroid.
So what are the main stresses we now have to track?
The three major stresses are circumferential stress, which is the dominant tensile or compressive one, radial stress, SR, and shear stress, tau. Interestingly, in most compact, thick sections like crane hooks, we often neglect the radial stress because it's so small compared to the circumferential.
Okay, let's consider curved beams with wide flanges, like those used in large rings for pipes or airplane fuselages. If the flange is very wide, the stress won't be uniform across that width, right?
That's a massive problem caused by shear lag. The shear stresses near the web prevent the remote edges of the wide flange from participating fully in carrying the load.
So you have to calculate an effective width.
You do. For an indefinitely wide inner flange, the maximum effective width B0 is calculated using the 1.56 square root of RT rule.
Let's make sure we internalize that. B0 is 1.56 times the square root of the product of the mean radius of curvature, R, and the thickness, T. This isn't just theory. This calculation dictates how much of that material you paid for is actually working.
Precisely. If you ignore shear lag, you grossly overestimate the stiffness and underestimate the stress in the flange near the web. It's a dangerous mistake.
And for thin tubular sections, curvature introduces another headache: geometric distortion.
Yes, thin rings are highly susceptible. Radial stress causes distortion that can drastically reduce both strength and stiffness, requiring an additional correction factor, K, in the formulas.
And there was a memorable detail to illustrate this.
A truly memorable one. Imagine a 1-inch thin pipe fixed at both ends, subjected to a heavy load. The theoretical calculation for the deflection resulted in a 20-inch total change in the horizontal diameter.
20 inches. That is an extreme, massive deformation.
It instantly highlights the limitation of linear elastic theory. If your calculation predicts a deflection that large, you know the underlying assumption that the loaded ring remains nearly circular has been completely shattered.
Your initial linear analysis is useless.
Utterly. You have to move to a large displacement, nonlinear analysis.
That sets the stage perfectly for our final section. We've established all the ways a beam fails within the elastic range. Now, let's discuss what happens when we intentionally push the material past its elastic limit, entering the realm of ultimate strength design, or plastic design.
This is the critical transition from worrying about the first fiber yielding to calculating the point of catastrophic collapse. Once the yield strength, SY, is reached, the failure moment is the plastic moment, MP, calculated by MP equals SYZ.
Z is the key here, the plastic section modulus. Explain conceptually what Z represents beyond just the math.
Conceptually, Z represents the moment required to make the entire cross-section yield. It's idealized as having half the area in tension and half in compression, both at the yield strength. Mathematically, it's the arithmetical sum of the static moments about the neutral axis of the parts of the cross-section above and below that axis.
So for a simple rectangle of depth D and width B, the plastic section modulus Z is 1/4 BD squared. It is purely a geometric property tied to the yield point.
Correct. And the phenomenon that enables plastic design is the formation of the plastic hinge. Collapse occurs not when the first fiber yields, that's the elastic limit, but when enough plastic hinges form to transform the structure into an unstable mechanism.
So it can rotate freely under load. And this leads to a fundamental disagreement between elastic and plastic analysis near the ultimate limit, the concept of moment redistribution.
This is the definitive distinction. Consider a beam fixed at one end and supported at the other with a center load. W elastic analysis dictates the maximum moment occurs at the fixed wall. But as the load W increases, yielding starts at the wall. Critically, as yielding progresses, that fixed wall can no longer hold the full elastic moment. The moment actually decreases at the wall and is redistributed to the center, where the load is.
The structure is finding a new way to carry the load, flexing its hidden capacity.
Exactly. Collapse only occurs when the moment at the wall and the moment at the center load both reach MP, forming two plastic hinges. The resulting collapse load, WC, is much higher than what elastic analysis would predict. 6 MP divided by L.
Which is why ultimate strength design is often more economical. It accurately accounts for the full capacity of the material.
That's the whole point.
We've covered a huge distance today, moving from the simple assumptions that govern straight beams to the nonlinear math required for combined loads and complex geometries, and finally, the ultimate capacity determined by plastic hinging.
The key takeaway for you is that engineering analysis must always adapt to the complexity of the structure and the loading. Whether you are using the beta factor to define foundation stiffness, adjusting loads for tapered sections, or calculating Z for ultimate strength, these specialized tools are essential.
Because basic theory would just fail dramatically.
It would.
So what does this all mean for you as you dive deeper into structural challenges?
Well, we talked briefly about shear lag in curved, wide-flange beams, but it affects straight beams too, particularly with short, stiff spans or thin elements. Your next step should be to fully explore the impact of shear lag in straight, deep, wide-flange beams.
Okay.
It's a consequence of high shear stresses near the web that severely limits how much of the flange is truly effective in carrying the longitudinal load, challenging that fundamental assumption of uniform fiber stress even in the standard elastic range. Understanding that mechanism is crucial for designing efficient, modern structures.
That sounds like a powerful way to end this deep dive. Until next time.